Hello, my name is Henry Bright, and this is the Project 1 simulation in Fluent for Fundamentals of Aerodynamics. So this is the details of the project on the screen right here. I'm just going to go through one case of how we model, particularly the turbulent case, but we had to simulate flow over a stationary cylinder with inviscid flow, viscous laminar flow, and viscous turbulent flow. And I will go through the case of the turbulent flow at a Reynolds number of 800,000. So let me go ahead and share the workbench. So we come to this screen, we start by opening up our fluid flow Fluent, and that's what I've done. And then we right click here and we open the design modeler. I've already opened it, so I'm just going to go ahead and share that. So here's our design modeler. So once we're in our design modeler, we're going to go ahead and sketch out what we need to get our surface so that we can start simulating some of these results in 2D. So we're going to start with the XY plane. Go ahead and click on the Z plane so we get a good look at the two-dimensional XY plane. And then we need to go to sketching. And we're going to click circle. This is what we're going to do for our cylinder obviously in 2 dimensions. It's just going to be a circle. We're going to click on that center point, so 0, 0. Go ahead and create our circle, and then we're going to dimension that with our diameter. The diameter given for this project is 1 meter. So we'll go ahead and change it to 1 meter. And then I'm just going to go ahead and delete this to get it off the screen. So you can see when we zoom in, we have our circle, diameter of 1 meter. Then we're going to go ahead and draw some lines so that we can create our meshing surface so that we'll be able to simulate the flow. And so that surface, we're just going to create a 50 by 50 meter square, but to do that, we're going to go ahead and create some lines from the center, horizontal lines out, and then we're going to do some vertical lines up and one down. I'll show you guys why in a second here. So we get those created, and then we're going to need to dimension those. So we just have our general dimension. I'll change those in just a second once we get those added. So once we have those, we're going to change all of those to 25. You're going to see it basically pop off the screen there because obviously we're very far zoomed in. You can see the scale. We'll change all of those to 25. And once we do that, we'll just go ahead and zoom to fit this. Okay, and now you can see it. So next thing we're going to do is go ahead and create a rectangle. Go back to draw and create those from our top point to our bottom point. This is basically going to create the 50 by 50 rectangle that we want. And then after doing that, we're just going to go ahead and delete these lines, including the ones we created, all the ones that we created before. Once we get rid of all of those, and we'll just create some new lines. So we have our 4 lines to create our surface for the meshing surface. So we click from this point to this point. And this one to this one. Okay, once that's done, we can go up here to concept and surface from sketches. And then we'll just open up from our XY plane. We want to click on that sketch 1. So that's got all of both the circle and the square that we created. We'll hit apply and then generate. And that creates our surface. If we zoom back in, you can see it's got that opening where basically the cylinder is being represented there. So we're just going to get our flow throughout this whole meshing surface once we create that mesh. And so that's going to be our next step, is to create that mesh. So once we go back to our workbench, here we are. You can see our geometry is checked off. We've got that done. So now we're going to go ahead and open the meshing. That might take a second to open up. Once we do that, then we'll be able to start creating the mesh. We're going to do We're going to add a method to our mesh. We're going to add edge sizing, and we're going to add inflation to create our mesh. And I'll go through all the details once this loads. So there you go. You can see our surface is loaded here. So we'll go ahead and go into the XY plane again. You can see it. And we're going to click on our mesh. So there that is. And then we're going to go ahead and right click on that, insert method. You can see it just comes up with, we need to select the geometry. I'm just going to click on this face. And we're going to go ahead and change this under method. We're going to change this to the triangles method, or the all triangles method. We'll go ahead and do that. And let's go ahead and generate that. There we go. So you should see something kind of like this. And the next step we're going to add is we're going to insert sizing. We're going to insert edge sizing. So we need to select our geometry again. Let's go. We got to change this to face. So we want our face. And then our element. Oops, did not apply that face geometry. Apply that. There we go. Oh no, sorry, I'm mistaken. I was getting ahead of myself. No, not the face. We want edge sizing, as I told you before. So we're going to go ahead and click on the circle. There we go. Now we have our edge sizing from our interior. So we're highlighting there. Okay. And then we're going to change this under type. We're going to do, we're just going to keep this under element size actually. I was going to say we could do number of divisions, but I think we'll just do element size and we'll just set that to 0.005. And then the other important thing to change here is to the hard behavior. That's going to be representative for what we're trying to do with the cylinder here. And then we'll go ahead and hit generate to update that. You can see, got our edge sizing there. Okay. And the last one we're going to do under our mesh, so we're going to right click on that again, insert inflation. And so for our inflation, our geometry again, and we're going to be doing the face this time. This was where I was getting ahead of myself because I clicked the face, the edge sizing, but that's actually what we want here. So we want that geometry, but then our boundary, we need to select the boundary, and that is going to be our edge in here. Edge and circle there. Apply that. Boom. And then we're going to change under inflation option. We're going to look at first layer thickness is what we want to define. And we're going to define that as 0.02. We will do 100 for our max layers and a growth rate of 2.5. Okay. And then let's go ahead and generate that. This will take a second. As we're adding some of these elements and starting to refine our mesh size, it's going to take us a little longer to load. We're just going to go ahead and up with that. And now you can see we've got a well-defined mesh here right around the boundary of our circle or our simulated cylinder, circle in 2 dimensions. And so the last thing we're going to do with our mesh before we close out of this is we're going to refine that mesh a little bit more. So our element size is currently just under the standard default, which is about like 3. So we're going to go ahead and refine this much, much more. We're going to go ahead and do 0.2. And let's generate that. That's going to take a little while. We'll go ahead and load that up. And then the one last thing that we'll do just in a second, once this finishes meshing, is while we're in here, we'll go ahead and define our boundary layers so that we'll be ready for that once we get to Fluent and actually simulating the flow. We'll need our velocity inlet, our pressure outlets, or inlet and outlet. We'll just need the 2 walls on the upper and lower surface. We're just going to, those are symmetry walls. And then the wall around the cylinder will just be our cylinder wall, is what we'll define that as. And so once we do that, once this is done, we'll go ahead and do that. So you can see our mesh is much more refined now, and especially right around the cylinder, you can't even see it, it's so dark. So you really zoom in. It's a nice, good definition of points. You can even check kind of the precision of your mesh by looking at your nodes and elements. Our statistics on there, so you can see very high. We want to keep these under 400,000. So we're good here. We should be able to get some good results, hopefully. So that's that. And then, like I said, we're going to go ahead and select our edges. So the front one, we're going to right click and we go to create named selection to do what I was saying. I'm going to do velocity inlet. Okay. Our right edge, we're going to write as our pressure outlet. Perfect. And then we'll click on both our top surface, and then I'm just holding control to hit the bottom surface as well, so that we name both of those. And we're just going to call those symmetry. And then our last one, I'll go ahead and zoom in as we click on this inner edge, selection, and that will be our center wall. Okay. So now we should be done with our meshing. And so what that means is we'll come back to our workbench. Should be able to see that now. And before we do anything else, we need to update this. So it updates with our new mesh that we've created. You can see it's got a check mark now, so we're good to go. And thus we'll open up our setup and move on to the next step. We're going to actually open Fluent. Okay, I'm not sure if you can see this first part that's opening up here. Okay, I'll share it in just a second. There we go. You can see these options open up. We're going to go ahead and do double precision. That's going to give us the best results, the most precision and accuracy. Change this to 4 just to make our computing lives a little bit easier and a little bit better. And we'll go ahead and hit start. So now I'm just waiting on the program to open. Everything is popping up, so it's going to take a second for me to be able to share the screen while the mesh is being generated and everything else is being done. It kind of kicked me off from trying to screen share. But here we go, we should be back. And so we will get our Fluent opening up and looking something like this. Okay, and here we are. You can see our mesh right there, and you can see our inlet and outlet. Everything looks pretty good. You can see the mesh there. Awesome. So we get into here under general. We're going to keep everything the same here. This is good. This is all what we want. We have a steady problem. One thing to note is with the steady problem, in the laminar flow case, when you're trying to simulate laminar flow, there can be some difficulties with the solution converging there. But that is just because generally laminar and steady flow have a little bit of issues being simulated here on Fluent. But anyway, that's not what we're going to be simulating in this case. So the first thing we're going to do is we're going to go under models and we're going to look at our viscosity. We're going to change our flow. So we have inviscid, which is for the first case of the project, laminar for the second case of the project, and our third case is our turbulent flow. So we're just going to go ahead and use the Spallard-Almaras. Keep all these settings just as they're defined. And that's what we're going to use for our turbulent flow simulation. So that is okay. And then the next thing we're going to do is we need to change our air properties. So we're going to go under materials, under fluid and air. We double click on that. And then, I don't know actually if you saw what I opened last time. Let's share. I don't know if you can see. Hopefully you can see pop up here in Fluent, where it just shows, basically it'll just show you air properties. And so we've got our density and viscosity. And so we've got our density is 1.225. We're going to keep that the same. However, for the viscosity, we need to change that so that we get a proper Reynolds number. So our Reynolds number is 800,000, which means that the viscosity that we need to use is 1.51325 times 10 to the negative fifth. That is going to give us our proper value. So we hit change create and then close. So we've got the proper fluid value and we're going to have the proper Reynolds number, because All of these cases are being simulated under a free stream velocity of 10 meters per second, which is what we're going to update in just a second. You can check under some conditions that you've got your fluid, air, and you can see that the properties are consistent, so that's good. And then we're going to look at our boundary conditions. So the first one, like I said, we need to add our velocity inlet. So we need to change this to 10 meters per second, which is exactly what we want. Okay, we'll hit apply and then close. And then the other boundary condition we're going to take a look at, we're not actually going to change, is our wall condition. So for this case, we're going to keep a stationary wall. The main three cases are all stationary walls, but then for the laminar case, we also need to do a moving wall. And so if you were to do that, you would click on moving wall and do rotational, and you would enter the rotational velocity, counterclockwise being positive, clockwise being negative. So in this case, we did -20 radians per second and -40 radians per second. In this case, we're just doing turbulent. So that's just one thing you would need to keep in mind and change if you're doing one of those cases. I'm not going to worry about that for this case. We check our reference values just to make sure that everything looks proper and everything matches with what we've been doing. And you can see we've got the right viscosity, velocity, density, all of that fun stuff is the same. So that looks good. Next thing we're going to look at is our methods, and we need to change these. So we're going to change our scheme to simple. Gradient stays as least squares cell-based. Pressure, we change to presto. Momentum, second order upwind, correct. We're going to also change our turbulent viscosity to second order upwind to match with that. So we have those settings good. Then we're going to take a look at our monitors and just make sure you can see we've got our criteria for convergence for the solution. Like I said, there's been some issues with the laminar flow, but our turbulent flow should converge. We're going to see in just a second. That looks good. About 10 to the -3rd is totally fine for this case. And then the next thing we need to do to get ready is we need to initialize. And so we're just going to do our hybrid initialization. We're going to come in here. We're just going to change this to 35 iterations. This to converge, and we'll go ahead and hit initialize. And you can see it is initializing, the values popping up. And there we go. Looks good. Awesome. And so now the last thing to do, well, not the last thing, but the last thing to run our calculations is to open up our run calculation. Yes, I know, so intelligent. But anyway, we're going to change our number of iterations to 1,000. That should cover us. The solution should converge before that. I know I used 1,000 for our laminar solutions as well, and the residual did kind of level out, but it didn't converge. So keep an eye out for that. And then we'll go ahead and hit calculate and run this, and you should see it start to run. We can look at our scaled residual plots. You can see it there. It's converging, appears to be converging slowly but surely. We'll see if that continuity continues to go down. I'm not 100% sure. We're looking on the right path right now, but it's converging at a reasonable pace for what this is running. I know my computer is running pretty slow right now, especially with screen sharing and whatnot. Now it's starting to level off a little bit. We may not reach convergence here. I know when I was simulating it earlier, I was using a slightly different mesh, and it was converging a little bit faster. So I probably should have done that. I could probably change that, but I think this will be okay for at least showing how to do this process. So you can see it's running, but our residual is really not converging. Kind of leveled off a lot. So that's a little bit unfortunate. But we will get some sort of solution. It just may not be as accurate as we were hoping. We'll just take a little while here because And then once we get done with this, we will take a look at some of the results, see how to pull those up. We'll look at the pressure contour, the velocity contour. You can actually find it both here in Fluent and under solution from the workbench, which we'll go over. So we'll have the graphics there. We'll have plots. We can get a plot of the pressure coefficient versus position. We can get a plot of velocity versus position. Keep in mind, though, for velocity, since this is a viscous flow, we have the case where there's a no-slip condition on the surface of the cylinder. That was one of the settings I should have pointed out when we were looking at the flow and looking at the boundary condition. But yes, that is the case. So we should get a flat response with that. And then other than that, we're just going to expect to see a little bit of a wake region behind the cylinder. Not as much as the laminar case, but we should see something of that. It's a very strange spike all of a sudden now in the residual. A little bit strange here. I'm not sure what's going on there. I'm not totally sure what the issue is right now, but we will let it run out just because I'm curious to see what it produces. It's not. It is getting worse and worse. This is not good. I'm gonna let this run out for now, but this is not the way it should be run. In my previous simulations, I've been having a lot better luck than this, so I'm not quite sure what's going on here. I know we did have one, I never mentioned it, but I know when we were meshing, there was a little bit of an issue where it was saying something about the tolerance around the boundary was being violated, I believe, and so that was a little bit concerning. But I know I've ran it before and usually not had an issue. Looks like there's some issue with the turbulent viscosity ratio. So not quite sure what the issue is there. We're getting a lot of variation in the results. So we're going to see what the results look like. They may not be super accurate, but you at least get a vision for the process of how this is supposed to work. And also another option could have been we could have made that mesh a lot smaller. A lot of times like a more rectangular mesh where it's not quite as tall can be good. But our calculations are complete, so let's take a look at our results. So the first one we'll take a look at is under graphics. We'll click on contours, double click on that. You can see this menu option pop up. Should be able to at least. And we'll go ahead and do shrink this down, move this over. But should be able to see we're going to do our pressure, static pressure. We're just going to do clip to range. Show the lines here, and we need to select all of the bodies there. Go ahead and compute. Yeah, we have some major issues, it looks like. These are not accurate. We've got incredibly high pressures, and that makes sense with that high residual. It seems like there's an issue. I may need to relook at this, because this is definitely not a good result. Let's go ahead and try to go. Let's check our inviscid flow and see if we get results that are a little bit better. All the conditions should revert back to what we need, so I'm just going to go ahead and initialize this. Should be fine. Let's go ahead and run the calculation. I'm curious to see if that will converge or if there's a bigger issue in flow. If it is converging, it's not converging as fast as I think it normally would. So This is a little bit troublesome. It may still converge. I'm going to give this a second, otherwise I might stop this. It does look like we're getting more favorable, but it's also converging pretty slow. It's a little concerning. This may not have been the best mesh, but it looks like we might converge here. Slightly optimistic. We just need to get to the negative third, and we're getting closer to that now, so it's looking like we're going to converge here, so we'll see if we get a better solution here. Bouncing back up and down with my continuity, so I thought we were getting close. Don't know if it'll fall back in, but looks like it. We're getting close, folks. This is frustrating, but this is looking much more promising. It might take a second more here, but we're getting very close. Maybe about 600 iterations or so. We should probably converge. But I might eat those words. I'm watching so intently, guys. This is nerve-wracking. It's like, please just converge. I'm not quite sure what all the issue is with the mesh or what might be the issue, but I did not have good solution versions. And there we go. Like I said, a little bit past 600. That is good. So let's go ahead and take a look now. We'll go back to our contour. I think it's still pulled up there, but that doesn't look right. It may need to be computed again. Yes, okay. Read some of this. Aha. There we go. Much better. Much more like it. That's more like what we should see. Beautiful. So I'm going to go ahead and run through, I'll just use the invested flow as an example here to just run through how this should look and what results you can get, even though this isn't the correct case that I was trying to go over. But I'll go ahead and show you, we can look at the velocity distribution or velocity contour as well. Compute that and then save and display. And there you go. You can see well, this is very expected for an invested flow. You have your stagnation points at the front and the back, and then you have your highest velocity at the top and the bottom, all well and good. So that's promising. The next thing we'll look at is plots. We're going to go to XY plot, double click on that. You can see our option to pop up here. Hopefully you can. And we'll look at our pressure coefficient is what we're interested with respect to position. We're looking just at the direction vector on the cylinder wall, so we got to click that, and we'll hit save and plot. And there you go. That looks very good. That's exactly what we're expecting. So you have maximum of 1, minimum of 3, and you get those points where you're going to have the lowest pressure at the top and bottom because, of course, and so position 0 along the x-axis because that's where you're going to have the highest velocity, sorry, and then obviously at stagnation points you have the highest pressure, so that's the 2 endpoints of the cylinder, so that's all well and good. We like to see that. And then velocity, I think I explained this earlier. Hopefully you know what you should be getting. Okay, no, I didn't, because I was talking about the turbulent case. So turbulent case and laminar case, we have a no slip condition. So on the surface, we're going to have 0 velocity unless we have our rotation. And so I would like to have explained that, but unfortunately, I don't have those results. Then you can see basically just our general shape where you've got the velocity is maximum at the top and bottom, and then you have your stagnation points at the front and back. So that's good. The next data that we can take a look at is our reports. and we'll go to forces. This is where we're going to get our lift and drag coefficients. So we use the direction vector to get those. So x1, y0 would be just a unit vector in the x direction. So that's going to be our drag coefficient. We click on our cylinder wall and we can print the results there. So you can see them up here. As you can see, coefficient pretty close to 0. That's what's expected because it's an inviscid flow. And then I can also look at the lift coefficient by changing this to 0 and 1. We'll go ahead and print that. Again, coefficient pretty low, close to 0 is what we would expect. And you can also write these to a file, which is nice. The only other thing I'll show is we'll go back to our workbench. And the last thing we can do is go to results. If we double click on results, I'll share that once that pulls up. So once we get our results, share this when this is pulling up. Beautiful. You can see this. We just get our plane. So what we can do is we can create our streamlines. We can also get our pressure contour and our velocity contour. I'm just going to show you the streamline on here since I showed you those on the other part of Fluent that we were looking at. So we're just going to our streamlines. We're going to start from symmetry 2. It's going to show us what we want, and we'll go to max points. Let's just start with 100 and just see what that is. Hit apply. No, we don't want surface volume. We want symmetry 2. Okay, that might be an issue. We get surface streamline, not 3D streamline. Symmetry 2 should be good. Let's look for once this loads. Okay, you can see we'll need many more points. Let's go ahead and bump that up to 200. And now we can start to get to see a better look at what we're looking for. If I zoom in here, we can do even more, but at least this gives you an idea. You can see what we're looking for, where you've got much higher velocity at the top and bottom, and you've got kind of your like stagnation points on the front and the back of the cylinder. There you go. You can get an even better picture. There. Again, this is the inviscid case, so this is a little bit different. But this at least gives us a picture of what we're looking for. So that should be pretty much all the results that we're looking for and that we're asked to find. That should kind of give you a good idea of what we're looking for. So hopefully this was helpful. Sorry about the issues with the solution not converging with the turbulent case. It would have been nice to show that, but hopefully you can figure that out on your own as well. So awesome. Cool. Hope you enjoyed.